All right, folks, get ready, cause today we're going to be looking at a paper called RoboPanoptus, the all-seeing robot with whole-body dexterity.
Oh, yeah, I know this paper.
It's a good one, right?
Yeah, this is one that really stood out to me.
Yeah, and it's pushing the boundaries of robotics, so, you know.
It really is, and I think one of the things that makes it stand out is how it challenges the conventional way of thinking about robots. You know, the kind of single camera, single end effector approach.
Exactly, like one eye, one hand, and, go from there. But this is like,
This is saying, hey, what if we use the whole body?
what if the whole body is both the eye and the hand?
Yeah, and they've got some really impressive results, with things like sweeping multiple objects at the same time, manipulating objects larger than the robot itself, unboxing in really tight spaces, and doing really precise multi-step stowing in cluttered environments.
Yeah. So before we get into all that, let's kind of map out where we're going to go in this deep dive.
Sure.
So first, we're going to talk about the robot itself, like the hardware, the algorithms, all of that.
All the nuts and bolts.
Exactly. And then we'll take a step back and kind of look at the historical context of where this fits in with everything else going on in the field.
Okay.
And then finally, we'll wrap up with our novel notions segment.
Always a favorite.
Yeah, where we brainstorm some
Yeah.
potential extensions of the research.
Sounds good to me. So let's start with the robot itself. What did they actually build here?
So picture this 9 identical body modules kind of linked together.
Almost like a snake.
Exactly. And then each module has an actuator to move 2 cameras for vision. And they do some really clever wire management to keep everything organized.
Oh, wow.
Yeah. And then on top of that, they have a head module with 5 more cameras of light and this hook-like end effector for more manipulation options.
I see. And that modular design is really interesting, right? Because you could theoretically scale up the robot just by adding more modules. You could have more flexibility and reach.
Right.
And it makes the hardware simpler too, more practical to actually build.
Yeah, like a robotic Lego set.
I like.
And then the camera placement is really strategic too. So they have cameras pointing outwards on all 4 sides of each module.
Okay, 360-degree view.
Yeah, and then the head module has those downward-facing cameras to eliminate any blind spots.
So it's like they've given the robot eyes everywhere. It can see everything it needs to do these complex movements.
Exactly, and that brings up the question of how do you even control a robot like this? With so many moving parts, you can't just program every possible scenario.
Right. Yeah, it would be impossible to program a specific set of instructions for every single situation.
So what they did was they created this leader-follower system where a human operator uses a leader robot to demonstrate a task, and then the follower robot mimics the leader's movements in real time.
Oh, interesting. So it's like teaching it a dance routine.
Yeah, exactly.
That makes sense, right?
Yeah.
Because with so many degrees of freedom, that would be a nightmare to try to program manually. But if you can just show it what to do, it can learn by imitation.
Exactly. And that's how they collect data for the robot to learn.
Okay, so we've got all these cameras feeding information into the robot, but how does it actually translate that visual data into movement?
So they developed this thing called a whole-body visual motor policy.
What is that?
So it's basically a neural network that takes the visual data from all 21 cameras, the robot's current joint angles, and then predicts a sequence of actions.
Okay, so it's learning to map what it sees to how it should move.
Exactly.
But I mean, we're talking about a lot of visual information here, right? How can it process all that and make decisions fast enough?
So they use a diffusion transformer.
Okay, now you're gonna have to explain that one to me.
So imagine you have a picture and you slowly add noise to it until it's like blurry and you can't even recognize what it is.
Okay.
So a diffusion model works in reverse. It learns to remove that noise and reconstruct the original image.
I see. So it's like taking a blurry image and making it clear.
Exactly. And in this case, they're using the diffusion transformer to take these kind of noisy predictions of the robot's future actions and refine them based on what it sees in its current state.
Oh, okay. So it's kind of like taking a blurry guess and then sharpening it until it becomes a clear plan.
Exactly. And the transformer part of the name comes from its ability to capture relationships between different elements of the data, like different camera views.
Okay, so it's not just about seeing what each camera sees individually. It's about understanding how they all relate to each other.
Right. And then they also use this thing called view-dependent positional encoding.
What's that?
So because all the cameras are moving around with the robot, they need a way to tell the network where each camera is located in relation to the robot's body.
Okay, so it's like giving the robot a sense of its own body.
Exactly.
I see.
So then they thought, well, what if some of these cameras fail?
Right. Yeah, that's a good point. You don't want the whole system to go down just because one camera has a problem.
Right. So they use this technique called blank training.
Blink training. Does the robot actually blink?
No, it doesn't actually blink,
Okay.
but it's a good analogy. So during training, they randomly drop out some of the camera inputs, simulating like a camera failure or a delayed signal, and this forces the network to learn to rely on information from a variety of cameras and be less sensitive to missing data.
Oh, that's clever. So it's like training it to deal with unexpected situations.
Exactly. Kind of like how humans can still function pretty well even if one of our senses is impaired.
Yeah, that makes sense. It's all about making the system more resilient.
Right. Okay. So all this is really cool, but I want to see how it actually works in practice.
Me too.
So what kind of experiments did they do with RoboPanoptus?
Well, they tested it on 3 different tasks: unboxing, sweeping, and stowing.
Okay. And each of those has unique challenges.
Yeah, each one requires a different kind of whole body dexterity, so it really shows how versatile the robot is.
All right. Let's start with unboxing. What was involved there?
Okay, so they basically had this box with a small hole on the side, and the robot had to figure out how to open it, which involved finding the hole, getting its body inside, and then lifting and sliding the lid open. And it's a good test of the robot's ability to work in tight spaces and manipulate objects with precision.
Yeah. And that hole being on the side must have been tricky visually, right?
For sure, because the robot couldn't just look down and see everything it had, to use those cameras all over its body to approach the box from different angles.
So how did it do?
It did really well. It had a 94.4% success rate.
Wow. That's impressive.
And they compared it to a bunch of different baselines, like a single overhead camera, a single camera on the head, and even versions of their policy without the positional encoding or the blink training, and none of them came close to RoboPanoptus.
It sounds like that whole body vision was really key.
It was the other systems either struggled to even find the hole, or they would get stuck following a pre-programmed trajectory and couldn't adapt.
So they were missing that contextual information.
Yeah, they couldn't really see the whole picture.
Okay, so whole body vision is good for unboxing. What about sweeping?
So for sweeping, they had RoboPanoptus sweep various objects into a target zone around its base. And some of the objects were on a table, but some of them were under a shelf, which meant the robot had to use its whole body to reach them.
I see. So it wasn't just about pushing things around. It was about using the whole body to manipulate objects strategically.
Exactly, and they compared it to the same baselines, and they also added another one. They had a person teleoperate the robot to move the small objects one by one, using only the head link.
Interesting. So a direct comparison between whole body manipulation and the more traditional end effector approach.
Exactly, and you can probably guess who won.
I'm guessing RoboPanoptus.
RoboPanoptus got a 96.6% success rate, and the single overhead camera only got 45.6%, and the teleoperated approach really struggled.
Wow, that's a big difference. So even with a skilled human operator, the end effector approach just wasn't as good.
Nope, and it wasn't just about the success rate either. RoboPanoptus was also way faster. It was almost 3 times faster at sweeping the objects than the teleoperated approach.
That's incredible.
Yeah, it really shows how powerful it can be to use the whole body for manipulation.
Okay, so we've got unboxing and sweeping. What about stowing?
So for stowing, the robot had to open a drawer, pick up a pair of shoes, put them inside, and then close the drawer.
Okay.
And they tested it with different types of shoes and even some other objects just to see how well it could adapt to different shapes and sizes.
Okay, sounds pretty complicated. How to do?
It did pretty well. It got an 83.3% success rate, and the other systems either failed completely or did really poorly.
So even for this more intricate task, RoboPanoptus still came out on top.
It did. It really shows that this whole body approach is adaptable to a lot of different problems.
Yeah, for sure. So it sounds like this whole body approach is pretty amazing, but are there any limitations to the current system?
Well, right now, RoboPanoptus is tethered to a PC for both computation and power. The researchers mentioned that in the future, they want to make it mobile, which would mean it needs onboard computation and a way to manage all those camera feeds without being physically connected.
Yeah, a mobile RoboPanoptus would be incredible. And what other future directions did they mention?
They talked about improving the efficiency and robustness of the computational side of things, which could allow for even more sensors or higher resolution cameras.
Wow, the possibilities are endless. Okay, so before we get to novel notions, let's take a step back and look at the historical context of this work. Where does RoboPanoptus fit into the evolution of robotics and AI?
Well, to understand this paper, I think it's helpful to look at a high degree of freedom robots,
Okay.
like SNCC robots.
Oh, yeah.
They've been around for a while. They're really flexible, really good at maneuvering in tight spaces.
Yeah, they can go through pipes over obstacles. Some can even swim. I've seen those.
Yeah, exactly.
But they're not really great at manipulating objects, are they?
No, not really. Their focus has been on locomotion moving around,
Right.
not manipulation interacting with objects.
So RoboPanoptus is kind of taking inspiration from them, but figuring out how to actually use all those degrees of freedom for dexterous manipulation.
Yeah, exactly. It's about more than just having a snake-like robot. It's about rethinking how we approach manipulation in general.
Yeah, and this is a big departure from the more traditional whole body robots, right?
Mhm.
Like you have the quadrupeds with the arms on top,
Right.
or the humanoids with legs. Those can move around, but they can't really use their whole body for manipulation.
Yeah, and even the ones that can, it's usually very complex and requires a lot of computational power to coordinate all those movements.
Right, whereas RoboPanoptus is using this more decentralized approach with the whole body vision.
Yeah, much more streamlined.
So it's interesting how they've combined elements from all these different robots into something really unique.
Yeah, it is. And I think the sensing aspect is important too. People have been working on giving robots a better sense of their own body and the environment, like tactile sensors, force sensors, range sensors.
Yeah, those are good for contact and navigation,
Hmm.
but not so much for the finer details of objects.
Exactly. And that's where vision comes in. It gives you a level of detail that you just can't get with other sensors.
So RoboPanoptus, with its 21 cameras, is really pushing the limits of what's possible with whole body vision.
It is. It's like giving the robot the ability to see not just what's in front of it, but all around it.
And most robots just don't have that.
Right. And that awareness is so important for whole body dexterity because it's not enough to just have a lot of degrees of freedom. You need to know how to use them effectively.
Okay, so RoboPanoptus is bringing together these different trends: high degree of freedom, robotics, whole body manipulation, and really advanced vision systems.
And it's changing the way we think about designing and controlling robots.
Okay, I'm sold. This is really cool work.
It is.
So now for the part that everyone's been waiting for, novel notions. What kind of crazy but plausible research ideas did this paper spark for you?
But this paper got me thinking about decentralized control in robotics. What if instead of having one central brain, we could give each module its own intelligence?
Oh, wow, like an ant colony or a beehive?
Exactly. Each module could process its own camera data and make its own decisions about how to move, and they could still coordinate with each other, but they wouldn't need a central processor for every single action.
That sounds incredibly difficult, but also really efficient, like a distributed nervous system.
Right. It could allow the robot to react faster and adapt to new situations.
I can see that, like, if the robot encountered a narrow passage, each module could just adjust based on what it sees, and the robot could squeeze through.
Yeah, exactly. It would be much more fluid, much more adaptable.
But wouldn't that require a ton of processing power at the module level?
It would, but that's where edge computing comes in.
Okay.
We're seeing devices like smartphones become incredibly powerful, so it's not crazy to think that we could embed that kind of power in each module.
That's a good point.
And here's another idea. What if we combine that with event cameras instead of regular cameras?
Event cameras, I haven't heard of those.
So event cameras, also called neuromorphic cameras, they don't capture frames at a fixed rate. They only record changes in pixel brightness. Oh, interesting.
So they're very sensitive to motion, and they can operate at much higher speeds than normal cameras.
So instead of a stream of images, you get information about where things are changing.
Right, and that would be really useful for dynamic tasks like catching a ball.
Yeah, so with event cameras and the decentralized control, each module could react to changes on its own, and the whole robot could move much faster.
Exactly. It's a really powerful combination.
This is amazing stuff.
But of course, there are challenges like developing algorithms for the event camera data
Yeah.
and coordinating all the modules.
Right. Challenges are what make research fun.
They do.
But before we move on, you said these novel notions are for entertainment purposes only.
Right, we can't predict the future. We're just speculating based on the research.
So these ideas might not actually happen.
Not necessarily, but hopefully they'll inspire people to explore these possibilities.
Yeah, for sure. Okay, so if you're interested in learning more about RoboPanoptus, we've got a link to the paper in the show notes.
And let us know what you think about the future of whole body dexterity. I mean, think about it. Robots like this could be helping with surgery or search and rescue in disaster zones or even exploring other planets.
Yeah, it's mind-blowing when you think about the applications.
Yeah, it really makes you think about what's possible with this whole body dexterity thing. But before we wrap up, I want to talk about something else that's been on my mind.
Okay, what's that?
Well, as these robots become more and more capable of doing things that we thought only humans could do, It makes me wonder about what it means for us.
Yeah. What are the implications for humans, right?
So how are we going to adapt to this new reality where robots can do all this stuff?
That's a really good question. And I think it's something we all need to be thinking about as this technology keeps advancing. The relationship between humans and robots is changing so fast.
Right. And we need to think about the ethics of it all.
Exactly. The ethical and societal implications.
Like, for example, what happens to all the workers if robots start taking their jobs?
Right. And how do we make sure that everyone benefits from these advancements, not just a select few?
Yeah. These are big questions.
Huge questions.
And there are no easy answers.
No, definitely not.
But it's important to have these conversations now.
Yeah, the more we talk about it, the better prepared we'll be for the future.
Absolutely, because it's not just about the technology itself, it's about how we use it and how we want to live with it.
I agree. It's about finding that balance between progress and well-being.
Will said this has been a really interesting discussion.
It has.
I feel like we've just scratched the surface, though.
Yeah, me too. There's so much more to explore with this topic.
But that's what makes it so exciting, right? Who knows what the future holds for robotics and AI?
It's going to be an incredible journey, that's for sure.
All right, well, that's all the time we have for this deep dive here on Talk Tensors.
Thanks for having me.
Thanks for joining us, everyone, and we'll be back soon with another fascinating paper.
Until then, keep those minds curious.
And those algorithms humming.